All right, so as we've been working our way through equilibrium, we've looked at various types of equilibrium. We've looked at equilibrium in very general terms. We've zoomed in and looked at some in specifics. And we've already talked about weak acids and weak bases in terms of the fact that they do an equilibrium. Now we want to look at how we handle the equilibrium. So that's what we're talking about today, is the weak acids, Ka and pH. And understand the weak bases, we're not going to spend a whole lot of time on that, none at all at this point, but they're going to be fairly similar, except the fact that they're a base, and we're talking about hydroxide instead. So, of the things that we're going to be using, we're going to be needing to know what a weak acid is and how to recognize a weak acid. And the good news is pretty much everything we're going to do is going to be a weak acid, but pay attention to it because sometimes it might be a weak base, right? Not today, of course. How we write the equilibrium expressions, because one of the downsides of weak acids is we can get kind of lazy and then we start to forget how to do equilibrium. And then how do we do a pH calculation? And of course, we're going to be using ice tables. And like all the other equilibrium type questions, there are two kinds of things we can do. We can use our equilibrium concentrations to figure out our value of K, the equilibrium constant, or we can use our equilibrium constant to figure out something about the concentrations. However, it is going to be a little bit different with with acids, because we're focusing on pH. So we don't necessarily need all the concentrations, just one. Okay, so let's start with Ka values. If I have an acid where I know the pH, and think about that, that's a pretty common or pretty understandable thing to do. I know the pH of my solution. I can use that to figure out the equilibrium constant K. So if I have a reaction and I'm using H-Pro as my sort of propionic acid, it's going to dissociate partially and to form those ions. If I work my ice table, as I always do, and I can use that to figure out how much, what my equilibrium concentrations are going to be, at least in terms of X. Okay, but here I know one more thing. I know the pH. Now pH doesn't directly tell me the concentration, but I can use it to find the concentration. So I can use that to find the concentration of hydronium ion. That also means that the other X is the same thing, the concentration of the propionate ion, and that also means that I can use it to find the concentration of the undissociated acid in its original form. And of course, because water doesn't have a changing concentration, I don't need to worry about it, and my Ka expression simplifies to this, throw my values in as I know them, and I end up with calculating the value of K. Pretty simple, pretty straightforward. So what do? I set up my ice table, I work my concentrations, I figure out my concentrations from the pH value, and then I use those, substitute them in, and find K. Okay, pretty simple. If I want to find the pH or predict the pH of a solution of a weak acid, if I have the original concentration and I know the Ka value, this one's going to be a little bit more involved. Also not crazy difficult, and it's going to take a fairly standard look each and every time, simply because acids dissociate by losing one proton. So I have got this as my my acid. I'm going to do exactly the same thing. I always try and start exactly the same way. I start with an equilibrium reaction, and I start with an ice table. Okay, so it's going to look kind of the same thing. Now the main difference here is I will not know the concentration of anything. I don't know the concentration of hydronium, I don't know the concentration of acetic acid undissociated, and I don't know the concentration of acetate ion. So all I can do is keep things in terms of X, but I am going to substitute them into my equilibrium expression. Okay, I also know what that is equal to, 1.8 times 10 to the exponent -5. Okay, at this point, I'm going to start the math. So I'm going to substitute my numbers in, or my values in terms of X, and I'm going to solve it as far as I can. Now at this point, I get a little bit stuck. We have two options for getting unstuck. So at this point, I can either simplify this expression or rearrange this expression. Might not be simplified. Rearrange this expression and use a quadratic formula. I'll show you that really quickly. The other thing I can do is something called successive approximations, which is basically a bunch of guess and check, although it's more systematic than just simply throwing numbers at it. That's where we're going to spend our time today. So quadratic formula, I would rearrange the expressions so that everything is on one line. I get rid of the x squared over top of anything else. I bring everything to one side, set it all equal to 0, and now I can substitute it into the quadratic formula where my values of a, b, and c are indicated. If I do that, I'll end up with two possible roots. One of them will not make any sense because it'll be a negative number. I only want the positive value. Then I can substitute that back into my original expression to find my values of x, which is my concentration of hydronium, which I need to find the pH. But we'll show you that part at the end of the other one. Successive approximations. This is going to feel a little bit unusual because you've never done anything like it. However, it's based on some really sound logic. So start exactly the same way. I'm going to solve for x, or at least isolate x a little bit. At this point, though, I'm going to do things different. At this point, I'm going to take the square root of both sides. Now, if you're thinking you cannot take the square root of the right-hand side because of the way the expression is, you're right, except this is where I'm going to do my guess and check. I'm going to make approximations for the value of x. And my first approximation is that x is really, really small, so that if I took my decimal 10, subtract a really, really small number, I would round that off to decimal 10 anyway. Okay, so I'm effectively guessing that x is pretty close to 0. Put that in, do the math. I end up with an x1, or my first x value. Yeah, my first guess and check is 1.342 times 10 to the exponent negative 3. Pretty small, but not as small as I was kind of assuming. So my next guess then is to make the assumption, or the guess, that x was that value, 1.342 times 10 to the exponent negative 3. Put that value in. Do the math, do the square root, I end up with 1.33 times 10 to the exponent negative 3. Now I want to point two things out. Number one is my second guess and check is not the same as my first guess and check, but it's not that far off of it either. Okay, so what I'm going to do is try this again, where my third guess and check uses the number that I calculated from my second guess and check. Put that number in and I run the math again and I end up with the same number. So the guess that I put in is the check that I got back. At this point, I can be confident that the value of x is at least very, very close to 1.333 times 10 exponent negative 3 because I guessed that number and I got it back. Okay, we're not done yet because we were asked to find the pH or predict the pH, not figure out a value of x, but x is the concentration of hydronium ion, which I can use to find the the pH. So put that in and I get a pH prediction of 2.875. Now if you're wondering how many decimal points do I have to run on the pH, fewer. I usually use about 2. On the guess and check, the successive approximations, I like to run about 3 because I want to make sure that that isn't changing much at all. Okay, quick summary of that. Because I run my ice table, I put my values in my equilibrium expression, I keep them in terms of x, rearrange and start to solve for x. Okay, get into this expression. And then I start my guess and check. You don't need to put in all of the math. So for example, if I were to do this, I would probably just have x1 equals 1.342 times 10 to the exponent negative 3. Then my next line would be x2 equals 1.33 times 10 to the exponent negative 3. And my next line would be x3 equals 1.33 times 10 to the exponent negative 3. How many times do I have to check? Keep going until it's not changing. And again, I like to run about 3 decimal places so that I know it's not changing. I'm not like rounding up too early. Okay, and then I use that value of x to find the pH. You'll notice what I'm not doing. I'm not finding the concentrations of the other things because I don't really need that. I was asked to find the pH. Okay, we'll get a lot of practice with that. I know that that doesn't feel normal because you've never done anything like that, and you've all done the quadratic formula before. I will say, though, that once you're comfortable with successive approximations, it's actually really efficient. And usually our first guess is pretty good because the weak acids are also very weak, so they dissociate very little at all. So it kind of works. We'll talk to you another time.